Welcome to the shape of space, matrices. This is the first lesson in a series of lessons related to matrices. And matrices are the second series of lessons in the shape of space collection of playlists. So we previously had a series on linear algebra. This series on matrices depends lightly on the linear algebra series. In particular, the very first lesson in linear algebra was about matrices and linear systems. I would review that if you're not familiar with multiplying matrices and adding matrices, because I'm going to assume that here. The series itself, The Shape of Space, has multiple playlists. I've completed this first one on linear algebra, and this is the first lesson, as I say, on the matrices series. Then we'll follow that with matrix calculus and several other playlists on related topics, which I'll be preparing after I finish this series here. This particular lesson has an overview of the series on matrices, and then we talk about three specific topics: quadratic forms, positive definite matrices, and the trace of a matrix. In the previous series of lectures on linear algebra, I discussed some of the basic concepts of matrices: addition, multiplication, determinants, inverses, eigenvalues, and eigenvectors, the Jordan form. In this series of lectures, I want to talk about some less common properties of matrices that we need for matrix calculus and other advanced topics. And unlike the linear algebra series, I'm not going to prove a lot of the results. They're kind of straightforward, but take a lot of space to write out, and I'm not sure they add that much to the discussion. So I'm going to focus on the stating the results and giving some intuition and some examples. A quadratic form, Q of x, is a polynomial in several variables, all whose terms are of degree 2 or less. The quadratic form can be expressed compactly in terms of an n by n matrix A and vector x, shown here in this format. And I'll give you an example in the next slide. The matrix A must be symmetric, in other words, it equals its transpose, for the quadratic form to represent a scalar valued function with well-defined properties. Quadratic forms are widely used in optimization, physics, and statistics. So let's have a look at an example. So we have a 3 by 3 matrix here. You notice it is symmetric. You have 3 here, 1, 1, minus 1, 1, minus 1. And your vector has 3 entries because the matrix is 3 by 3. So if we multiply this out, we can first multiply the vector x times the matrix, and we get a 1 by 3 times a 3 by 3, we get a 1 by 3 vector, which is this here. And then we multiply this times the vector x in column form, and we get this here. And you notice that each term is of degree 2 or less. And when you have two variables multiplied, two different variables multiplied together, that still counts as a degree 2. So you have another degree 2 here. You notice nothing is more than degree 2. A quadratic form, Qx equals x transpose Ax, is not a linear transformation. For example, if we take Q of Ax, then plugging in Ax for x, we get Ax transpose times matrix A times Ax, and that gives us A squared Qx, and it would need to be just an A here if we had a linear transformation. So we violated one of the properties of a linear transformation. Changing directions a little bit here, we have another related idea. For a linear transformation such as AX, the equation AX equals 0 does not necessarily imply that A or X equals 0. But I have an example here. This matrix nor this vector, column vector equals 0. But when you multiply these together, you get 0, 0, 0. So that is an example of this here. However, if AX equals 0 for every X, then A must be 0. Every X in our vector space under discussion. Now, I'll talk about that more on the next slide. Related to the quadratic forms now, the situation is different. If you have a quadratic form, X transpose AX equals 0, even for every X in the vector space, it doesn't imply that A equals 0 or X equals 0. I have an example here. You have the row vector X times this matrix times the column vector X. In other words, something in this form. Then you multiply this and you get minus x2, x1. And then when you multiply these two together, you get two terms that cancel each other out. The following theorem relates to some of the points we made on the previous slide. AX equals 0 for every X in vector space under discussion, which is typically the Euclidean end space for the discussions here. If and only if A equals 0. X transpose AX equals 0 for every X if and only if A is skew symmetric. In other words, A transpose equals minus 1 times A. And X transpose AX equals 0 for every X and A equals A transpose if and only if A is the 0 matrix. So we're going to prove these in the forward direction. Going in the opposite direction is easy, and I'll leave that as an exercise. So let's look at the first one. Let X equal E sub I, where that's the column vector with a 1 in position I and zeros everywhere else. In that case, we have that A times E sub I equals 0 for every I, but A times E sub I is actually the column I of A, and thus, if every column is 0, then of course A is 0. And to help you visualize, I put an example of a 3 by 3 here. So here's our matrix A, and then this would be E sub 2. We have a 1 in the second position. And you notice if you multiply this out, you're going to get A12, A22, multiply this times this, you get A32, and this is the second column. So that's sort of an example of what I'm saying here. Okay, and if you get stuck on any of these proofs, it's usually easy or helpful to either do a 2 by 2 or a 3 by 3 matrix and run through the idea and just to convince yourself. So for the second item, we'll let X equal E sub I plus E sub j, where it's this vector is defined as before. Then we'll plug that into our formula. So we do that here. Then the transpose of a sum is just the transpose of each one individually. So this implies this. And then we use the distributive law twice, or once here to multiply this times A, and then to multiply these times the product of the first two. And we get this here. So we get 4 terms equals 0. And if you actually work through these, again, you might want to do a 3 by 3 just to convince yourself. But this first one here is AII, in other words, the term in the ith row, ith column of A. Then this one here is AIJ. This is AJI, and the last one is AJJ. So these are just scalars, and they equal 0. Right, that doesn't give us this yet, but if we set I equal to J, then we'd have JJ all the way here. We'd have 4 times AJJ equals 0. In other words, AJJ equals 0. So whenever you have the basically the diagonal element equals 0, so AII as well as AJJ equals 0 in this formula. So this term and this term drop out, and you get AIJ plus AJI equals 0. In other words, A transpose equals A minus 1 times A. Right, this is effectively A transpose here, and then you can just subtract this from the other side. Okay, so that was the second one. Then the third one is we were given 2 properties here, this and that A equals A transpose. So since this is true, we know from the second part of the theorem, which we've just proven, that A transpose equals minus A, and we're given that A equals A transpose. So in other words, A transpose equals this, A transpose equals this. So A equals minus A, and that can only be if A is 0. So that gives us the third part of the theorem. And as I say, you need to prove it in the other direction, but that's easier, so I'll leave that as an exercise. There's a couple of ways, at least a couple of ways, we can make use of the theorem from the previous slide. 2 points here. Concerning part 1 of the theorem, suppose we wanted to prove 2 matrices A and B are equal. You could do that a couple of ways. One is a direct approach where you show that Aij equals Bij for every ij, in other words, for every entry. Another way of doing that is to show Ax equals Bx for every x. In other words, show that A minus Bx equals 0 for every x, which in turn implies that A minus B equals 0 and then A equals B. So we have an alternate way of proving the 2 matrices are equal using part 1. And using part 2, we can do something similar, although it's not exact equality, but we can make a statement about 2 matrices. If the quadratic form was A and B are equal, in other words, if these 2 are equal, we know it's not necessarily true that A equals B, but if we subtract these, we get X transpose A minus B times X. Then from part 2, we get that with a little bit of algebra, we get that A plus A transpose equals B plus B transpose equals 0. So you need to do a little bit of calculation to get that from the part 2. I'll leave that as an exercise. Further, if A is symmetric and B is not necessarily symmetric, so if we just have A equals A transpose, but not for B, then we can still say something that it still does not follow that A necessarily equals B, but it does follow that 2A, basically adding, since A equals A transpose under this additional assumption, 2A equals B plus B transpose, or A equals 1/2 B plus B transpose. Okay, so these things are useful in some of the work we'll be doing later on in a subsequent series on matrix calculus. So I'm just pointing them out here. I'll refer back to them as needed. We have a few definitions on this slide that I'm going to use later on. And since they're related to quadratic forms, I thought I'd do them here. And then I can refresh your memory when we get to them at some later point in these lessons. A symmetric matrix A with real entries, real valued entries, is said to be positive definite if the real number X transpose AX is positive for every non-zero real column vector X. We have a similar definition for complex matrices. A Hermitian matrix B, in other words, a complex matrix equal to its conjugate transpose, that's taking the conjugate of the transpose of B and then taking the conjugate of every element in the transpose, is positive definite by definition if the real number Z star BZ is positive for every non-zero complex column vector Z, where Z star denotes the conjugate transpose of Z. So let me back up and further explain a few of the points in here. This is a positive, this is a real number, a scalar. You may have deduced that earlier, but I'm going to emphasize it here. X transpose is 1 by n, A is n by n, so when you multiply these together you get a 1 by n. And then when you multiply that times something that's n by 1, you just get a 1 by 1 entity, which is a scalar. And the same thing holds here, even though you have complex numbers, you would get a complex scalar when you multiply these out. That's one point. Another point is that, as a refresher, if Z is a complex number, A plus IB, where I is an imaginary number, the square root of minus 1, then the conjugate of Z is A minus IB. And then you may be asking, why is this a positive real number? And that's because when you take its conjugate, which I've done down here, it equals itself. And if a real number, if a complex number equals its conjugate, the only way that can happen is if the imaginary part equals 0. In other words, it has to be a real number. So this needs to be real. And just to go through the calculation here, if you take the conjugate transpose of this, you just put these in reverse order and then take the conjugate of each entity. So you get Z conjugate, then B conjugate, and the conjugate of the conjugate, transpose conjugate of the transpose conjugate, I should say. Then this is just carries over, but we're told that the conjugate transpose of B is equals B. That's by the definition of positive definite. And then the conjugate transpose of the conjugate transpose of Z is just Z. So this equals this, and then the argument that I just mentioned follows. It has to be real. Then we have some looser conditions here. Positive semi-definite is if you have for every x, this entity, this quantity here is positive or 0. So it allows for 0. Here you had to be strictly positive. And then you have negative definite and negative semi-definite. They're defined in a similar way. I won't go into that specifically, and I don't believe I use those either. And finally, a matrix that is not positive semi-definite and not negative semi-definite is sometimes called indefinite. I have some results on this page that I'm going to state without proof. A matrix A is positive definite if and only if it satisfies any of the following equivalent conditions. A is similar to a diagonal matrix D with positive real entries. So in other words, we have this relationship A, P is an invertible matrix, and D has positive real entries in its diagonal. Second condition equivalent to positive definite is A is symmetric or Hermitian, so that's in the complex case, and all its eigenvalues are real and positive. And we talked about eigenvalues in the linear algebra sequence of lessons. A is symmetric or Hermitian, and all its leading principal minors are positive. So this is a bit obscure, but let me try to explain this. So what is a minor of a matrix? A minor is that you remove a row, say row 3, and a column, say row 1, and then you form a matrix with that column and row removed, and take the determinant. And then it's saying that they need to be positive. Now, a principal minor is you remove the same, the number of the row and the column that you remove are the same. So you remove column 2 and row 2, and then you take the determinant, and that has to be positive for all the principal minors. I think I may use this later on in the sequence on matrix calculus. Again, I'll have to come back to this and refresh your memory if I need to use it again. Then the last equivalent is there exists an invertible matrix B with conjugate transpose B star such that A equals B star B. Okay, so all four of these are equivalent to A being positive definite. Then I have a definition here, which I think I mentioned already, but I'll emphasize it again. The conjugate transpose of a matrix, also known as the Hermitian transpose of an M by N complex matrix A, is an N by M matrix obtained by transposing A and applying complex conjugation to each entry. Yeah, so I mentioned this before, but just define it formally here. We have one more concept in this lesson, that's the trace of a matrix. It's defined pretty simply. The trace of A square matrix is the sum of the diagonal elements. The trace is a linear transformation, so if you take the trace of a scalar A times matrix A plus a scalar B times matrix B, you get A trace A plus B trace B. And we have these additional properties. I'm just going to state them without proof, although I guess the first one is pretty immediate. The trace of A equals the trace of A transpose. If you take the transpose of a matrix, you have the same diagonal elements, and so of course the trace would be the same. If A and B are two M by N matrices, so not necessarily square, then these different products are square matrices. They're not the same size, but they are square matrices. Some of them are M by N, and some of these are N by N, but they all have the same trace, so that's sometimes useful in a proof. And then if A and B are M by N and N by M, real or complex matrices whose product is thus square, we have the trace of AB equals the trace of BA. Then we have another property down here. The trace of the outer product is equivalent to the inner product. So the outer product is this here, where you take a column vector times a row vector. So it's 2 by 1 and 1 by 2 in this case, and you get a 2 by 2 matrix. And then the trace would be the sum of these two here. Then the inner product is you multiply a row times a column vector, and you get this, and you notice that's the same as the sum of the diagonals here. We have a few more properties of trace on this slide. The first one is the similarity invariance. So if we have A and we have P inverse AP, the trace of those two equals, where P is an invertible matrix and A and P are both square matrices of the same dimension. We can prove that here. We take the trace of P inverse AP, we group A and P together, then we can commute the order of these two. That was from our theorem on the previous slide, trace AB equals trace BA. And then once you have this, you just have P inverse times P, that's the identity, times A, and you get trace A. Then there's something called circular shifts. So the trace of A, B, C, D, you can shift that to the right, and then move the D up front, and it equals the original. Then you can shift again to the right, and move the C up front, and you do it again. And you can shift to the left, and you also get the same value for the trace. And it's not just for 4 matrices, you can have 5 or 6 or 3. It works in all those cases. However, you just can't do any permutation. So the trace of ADBC, there's not a shift of ABCD either to the left or right. And so these two are not necessarily equal. Then finally, we have the trace is the sum of the eigenvalues of a square matrix A added to multiplicity. That means if an eigenvalue appears, has multiplicity k, algebraic multiplicity k, then it needs to be added k times. This result holds true even if A is a real matrix with complex eigenvalues. And I'm not going to prove it in detail, but this follows from the existence of the Jordan canonical form along with this similarity invariance property. Okay, so that's the last slide in this lesson. I'll give you a number of references in the information to this video, and then I'll have several more lessons in this series on matrices.